Let's look at collective communication and the new non-blocking collectives that were added in MPI 3. So if you have done MPI programming, you're probably already familiar with collective communication. It's an important communication feature or functions in MPI because for performance, you need to use them. So the basic send receives are called point-to-point communication because you have one process doing a send and doing a send to a specific destination, which is a target rank in the send. So it's point-to-point between a pair of processes. Collective communication are functions that are called by a group of processes in the communicator passed to those to that function. So for example, if you do an MPI broadcast operation, it takes a communicator as an argument. That communicator specifies a group of processes. Everyone in that communicator must call that function. So it's an operation that is collective over all those processes. And in this particular case of a broadcast, the broadcast specifies who is the root of the broadcast, that is, who is the sender, and everyone else becomes the receiver. So when you call MPI bcast, one of the arguments is the root, which could be rank 0. You specify the root, and that's rank 0 in the communicator that you pass, which could be MPI com world, in which case everyone is participating. So the root sends the data and everyone receives it. MPI internally would do that in some optimized way. So a simple way is that the root just sends one by one to everyone, and then they will get the whole data. But that would not be very efficient. That's an order n operation, linear. That's what you might do yourself. If you had to send data from one rank to everyone, you might simply just send it one by one to everyone, which is not a very good way. MPI bcast does it in a sophisticated way. If you look at our MPI implementation, you've downloaded it, you can look at even the code that is used. So in the src MPI COLL directory, all these collectives are implemented. And you'll see that they use a number of algorithms. So it's not one algorithm for a collective, but depending on the message size and the number of processes, it picks different algorithms and tries to do it efficiently. So for small messages, it might use a tree, a logarithmic algorithm that is like a tree. The root sends to some process, and then you now have two roots effectively, and then they send to another process. So it's a tree-based binomial tree algorithm for short messages. For long messages, we use a different algorithm that optimizes bandwidth. It does a scatter and then all gather internally. So all that happens underneath the covers. The bottom line is that you need to call this kind of function. So another function is Mpi Reduce, which combines data from all processes in the communicator and returns the result to the root with an arithmetic operation performed. So let's say you want the sum of all values on all processes, and you want the result returned to a single process. You call Mpi Reduce with Mpi sum as the operation, and it will do that sum for you and give you the result. There's also all reduce, which will return the result to all ranks. So in many of your applications, there is opportunity to use these collectives instead of just send receives, and you're probably already doing that if you're running at some scale. As I said, communication it gets coordinated among the processes in the communicator internally for you. There are no tags. So if you look at the parameters to an MPI broadcast, there is no tag parameter. The point-to-point communications, they have a tag as one of the parameters. And if you have done sends and receives, and if you look at the code, there is a tag value, and there is a matching of these sent messages and the posted receives based on the tag. You can also use the MPI any tag wildcard on the receive side, which says match it with any tag. But none of that exists in collective communication. The collectives are automatically ordered in the way they are called. So if you do 3 broadcasts in a row, then those are the 3 broadcasts in a row, and the matching happens in the order they are called. And you have to make sure that you have not called them out of order. So if you call broadcast on one, you cannot call reduce on the other, or even receive on the other. So a common user error is the root calls MPI broadcast, and everyone else is calling MPI receive, as if they're receiving that broadcast. So that's a bug. That program will fail or in a block or hang or something. So everyone must call broadcast. Automatically there's a send happening internally on the root side, and everyone else is effectively doing a receive. Until MPI 3 or prior to MPI 3, there were only blocking operations in the collective. So MPI broadcast was blocking in the sense that it returned only after the operation locally completed. That is, if the root was doing a broadcast, it would send the data in some way and return. It doesn't mean that everyone else got the data. So blocking only means it is a locally blocking operation. We'll get into it in a little more detail. But MPI 3 has now added non-blocking versions of all the collectives. And that's implemented and already in MPitch, you can already use it. So there is an I bcast, and there is an I reduce, and I all others. They return a request object, and then you can do the test and wait, et cetera. And we'll look at it in some more detail. So in terms of how the collectives are organized roughly, there are three classes of operations. There are collectives that do synchronization. Actually, it's just the barrier that does the synchronization. And then there are collectives that do data movement, and that is the broadcast and the gather, scatter, and so forth. And there are some collectives that also do computation in addition to data movement, and that is the reduction and the scan type of collectives. So let's look at the first one, the Mpi Barrier, which is simple. It just takes one parameter, which is the communicator. And what it says is that this Mpi Barrier will block until all processes in the group of the communicator have called the barrier. So it's simple. It's if you want to get to a known state, by known state I mean you want to get to a point where everyone has reached there, you can call Mpi Barrier. So what it means is that a process cannot get out of the barrier until everyone else has reached the barrier. So when one process exits the barrier, you can be sure that everyone else has at least entered the barrier. They may not exit at the same time, but they have definitely reached there. I want to mention that in an MPI program, you don't really need to call a barrier. It's very rarely necessary in your program. But people sometimes for debugging, or if they're not sure of what's going on, they might just throw in a barrier in there, and it's usually bad practice, and it can be a performance problem because you're simply unnecessarily synchronizing your code by inserting these barriers. So one way to, the first thing you should do is look at your code and remove any unnecessary. For debugging purposes, it's fine. If your code is not running and you want to get to a known state, fine. But if you're running in production, remove all these unnecessary barriers in your code. In fact, our colleagues at University of Utah have a tool that can check your code and point out that this barrier is really not necessary. You should consider removing it. So application codes have these things that can be removed. One use of a barrier is just if you're doing some timing measurement, the way you do it is you call MPI W time, which returns the current value of the clock. And then at the end of whatever you want to measure, you also call MPI W time, which returns the value at that point. And then you do a difference, and that's the time taken by that operation. So you often want to call an MPI barrier before the first call to this MPI W time, just to ensure that all processes have reached that stage, and everyone has started the operation. So that's okay to use barrier in that case. But other than this, unless you really know what you're doing, so Bill mentioned in his slides that there was some case where you could use a barrier just to order the operations. So that's an advanced use. So you know what you're doing, you're deliberately inserting a barrier, that's okay. But other than this timing, you're adding it before the timer, and of course, this is when you're doing timings. If you're running something in production and you're not really measuring time, you can comment this out or if def it out so that there is no barrier here as well. So it's there, but it's rarely necessary, and if you're using it, ask yourself, do you really need a barrier here? The next set of collectives are the data movement. So the simplest is MPI broadcast. What it says is if this is the root of the broadcast and it has some data value value is not necessarily one variable. You can have a large array, whatever. You can, it's the usual buff count data type. So it could be any size. At the end of the broadcast, everyone gets that value, the same value. There are other operations. There is a scatter, which what it says is, if there is an input array on the root, and by the way, the root can be anything. The root can be 3, 2. You get to specify the root, and the collective algorithm takes care of it for you. The scatter says a portion of this array will go to each process. So if rank 0 has A, B, C, D, and there are 4 processes, then they will get a fourth. So this one will get A, this one will get B, and C and D. So it's a subset of a broadcast. A broadcast is everyone gets all the data. Here, effectively, the data is divided. So the way the function is called, it's not really divided. The way it's defined is in MPI scatter. It's a buff count data type. What it says is it takes the first count elements of the buffer and sends it to 0. The next count elements and sends it to 1, and so forth. So a smaller amount of the data is sent to different processes. The opposite, or if you can do the data movement in the other direction, which is a gather. So if you have different data on different processes and you want to collect it all on one process in the form of a concatenation, so A, B, C, D will get concatenated and placed next to each other in the root buffer on the root side. So these are just opposites of each other. If everyone wants the result, so the basic gather and the scatter is from, the gather in particular is from everyone to one root destination. Now, everyone may want the result, so you can call all gather. So the functions that have all in their name means everyone gets the output. Each one has its own contribution, and the result is being placed on everyone's buffer. And the other collective function is an all-to-all. The difference here is that each process has a unique data item to send to every other process. See, the difference here is that everyone gets A from rank 0. So rank 0's contribution to this is just A, and everyone gets that A. Here, rank 0 has a different, for 0 it wants to send A0, and to 1 it wants to send A1, and then to 2 it wants to send A2. And so it's a unique contribution from each rank to every other rank. So in terms of implementation, this is easier to implement because it's the same data value. You can use a tree algorithm and send it nicely everywhere with more efficiently. This is harder to implement because you have to make sure that the right data is getting to the right place, and it's all different data. See, broadcast is easy to implement because it's the same data going everywhere, so you can just propagate it. Here, this is more difficult. So codes that do all-to-all probably, they have more difficulty scaling. So one thing to look at is, does your code really need all-to-all, or can you do something else, or can you use a different algorithm that doesn't use all-to-all? Those are more advanced uses of MPI to think of things like that. And then in the case of collective computation, so this is Mpi Reduce. What it does is it takes the data values from different processes and performs an arithmetic operation on them. Let's say it's a sum, so it will do an A, so it's A plus B plus C plus D. The value of that would be returned to the root. And there are a whole variety of these operations, and I think that's on the next slide. There is also a scan operation, which is also known as a parallel prefix operation. So this is different in that each process doesn't get the sum of the whole thing. It depends on your rank. So rank 0 will just get A, which is the same as the input. There's nothing happening here. Rank 0 will get the A plus B, or A whatever is the operation with B. Rank 2 will get the A plus B plus C, and then the rank D will get the whole thing. And there's also another version called exclusive scan, EX scan, where the rank's contribution is not counted. So the B will just get B, and C will just get the result of A plus B, and so forth. So the scan and EX scan are used in parallel algorithms, and there's some literature on where they are useful and so forth. Then they don't tend to get used so much in in numerical applications, but it's there. Reduce and all reduce are quite widely used, and there's also a reduce scatter. Just to summarize, there are many of these collective operations. We looked at all gather, we looked at gather, broadcast. All reduce does a reduction and returns the result to everyone, not just the root. Then there are these V versions of the collective. So all the collectives, not the bcast, but all these gather, scatter, they also have what are known as V versions. So the difference there is here everyone gets the same amount of data. So we are doing a regular scatter here where everyone gets the same amount of data. So you can just use a single count value to indicate to in the function call. But if you wanted to send a different amount of data to each process, there are these vector V versions of the collective. So it's a scatter V or a gather V, where you have to pass a vector parameter saying, okay, rank 0 gets so many counts and rank 1 gets so many counts. So there's a parameter there that is of size equal to the number of processes in the communicator that has these different counts. So it's for the variable count scatters and so forth. And similarly for the all gather, there's an all gather V. There's an all to all V. There's even an all to all W where you can send, in addition to different counts, you can send different data types as well. So that facility also exists. So as you can notice, MPI is not a minimal API. It has everything that you might need. You don't need all of them in your code all at the same time, but whatever you want to do is there. And it's better to use the function provided than make something up on your own to do that operation. So as I said, all delivers results to everyone. The V versions are the vector, allowing the sizes to be different. And the reduction operations take both predefined reduction functions, or you can define your own reduction operations as well. So the predefined operations in MPI are things like MPI max and min. So if you want to find the maximum value on all processes, you use MPI max, and then min and prod sum, logical OR, bitwise OR, all these operations are there. There's also one called max lock and min lock, where you can not only find the maximum value, but you can find where is that maximum value located. So if you want to find out, say, which rank has the maximum value, there's a way to do that using max lock and min lock. So these are all already defined in MPI, but you may want to do your own, you may want to do something slightly different. It doesn't have to be something very crazy. It's just something that may not be covered in those operations. So you can create your own reduction operation and pass that as a function to MPI. So the way you do that is you call MPI op create, where you pass your function here, and it returns a type known as an MPI op type, and then you can pass this op to MPI reduce instead of the MPI max or MPI sum or any of the others. This parameter is for you to indicate whether this operation is commutative or not. That is, can the operations be, if you're doing A op B, can it be done as B op A or not? Can the MPI implementation do that or not? So you say 1 if it can be and 0 if it cannot be. So you have the choice of your function need not be commutative if that's what you want to do. The predefined ones are all commutative. These operations are required to be associative. That is, they could be done in any order of, if you're bracketing them. And the reason all this is there is, suppose you're doing this on 10,000 ranks and we're doing a reduction. Internally, we'll use some algorithm and we'll try to do them concurrently in parallel. We want, if it is commutative, we might just do them in any order, anywhere, as fast as possible and get you the result. If it is not commutative, then we have to be aware of that. You cannot do it in the reverse order, and so some optimizations may not be done in that case. So that's why these thing is there. So the user function, it is allowed to not be commutative, but it must be associative. So all reductions have to be associative. Let me go on to non-blocking collectives. So non-blocking collectives were added in MPI 3, which means last year. So MPI 3 came out last September, and MPIT supports MPI 3. So our release in supercomputing last year supports MPI 3. So you can try it on the laptop. It may not work on the blue gene. I don't think the blue gene MPI has supports MPI 3 features yet, but sometime later this year they plan to. I mean, they have access to our code, but they have not included that in the product version. So the idea here is to combine non-blocking features with collectives. So what is the advantage of non-blocking is that you can avoid deadlock. So you don't get into the situation of all the blocking sends are posted, and the one that the Bill talked about, and some of you encountered it during the hands-on, that if you just call the sends first, it can block. And you can potentially overlap communication with computation because you have issued the operation, and if possible, the system is going to overlap it for you. And of course, you want to use all the collective algorithms. This just combines the features of this, and there was demand from applications for this feature, so that's how it was added. So what I mean by overlapping is, suppose you issue a non-blocking communication, be it a point-to-point or a collective. That is somewhat issued, I mean, you've asked MPI to go ahead and do it, but you've not waited for it to complete. And then you've gone ahead and done some computation. It is possible for MPI in the background to do that communication for you if it works on if your system supports that, if the hardware and software allows that. You issue a non-blocking, and at some point you call MPI test or wait to make sure that the operation is completed. If there is no overlap, it will happen in the MPI wait, or it could happen during some other MPI function that is called. So when you call an MPI function, it doesn't just do that particular operation that you have called. It goes into what is known as the Mpi Progress Engine, which is the internal within the MPI implementation. And there it may have to do more than just what you have asked, because there could be some prior things that need to be done. So it's going to start doing some additional work. So it might get completed during some other MPI operation, but it will definitely get completed when you call MPI wait. So the question is, where should you call MPI wait? So you should call MPI wait as late as possible, because at some point you will need to know whether the operation has finished or not, so that you can reuse that buffer. When you call MPI isend and you pass that buffer, you cannot modify that buffer because that send has not completed. The data is still being sent. So at some point you will need to reuse that buffer because you're finished with this iteration or whatever, and in the next iteration you use that buffer or whatever. So that's when you call MPI wait. So that's the latest where the non-blocking operation will complete. The semantics are simple for the non-blocking collective communication. It's similar to the isend, which there is a request object that is returned, and then if you want to just test for completion without blocking, you can call any of these test routines. So there is a single request, you use test. If you have multiple requests, you can use any of these. This will just wait for any one to complete. This will wait for all, not wait, it will just test whether all of them have completed, and this is for some of them. And similarly, this is the blocking wait. If you do not want to return from the function until the operation is completed, you call the blocking wait operations. So the same thing is used for the non-blocking collectives. So there are these I versions of all the collectives. I stands for immediate, by the way. That's how that I came about in MPI. So the usual broadcast arguments, and it returns a request. And the semantics are defined that the function will not block, so it won't just wait there for somebody else. What does blocking mean? That it means that it won't be dependent on the actions of some other process. It will return locally. So it might initiate the operation, it might just queue the operation, it will do something. You cannot do something on some other process that will cause this to wait. That's basically what non-blocking means. So it'll return. What no guaranteed progress means is this, whether there's actually overlap of communication with computation or not. That is, you have issued this non-blocking broadcast. Does it happen in the background while you're doing something, you're doing your surface computation or whatever? There is no guarantee that something will happen in the background. That's up to the MPI implementation. What is guaranteed is that when you call the corresponding test or wait that is supposed to complete that operation, it will complete there. Of course, MPI will try to do something in the background, and particularly when you call an MPI function to do something else, it might go and poke what we call poke the progress engine, which means it will do some more of that operation. And they could complete out of order, in the sense that if you have called 6 of these collectives, non-blocking collectives, the order in which they complete is not, the smaller ones might complete first, or the easier ones might complete first, and so forth. There are no tags again, so you have to call them in order. So if you call a broadcast, IB cast, on the others also you should call an IB cast, not an I reduce or something. Even though they are non-blocking, they are expected to be called in order. And if you're doing 5 of these I broadcasts, then they're supposed to match in order. So this I broadcast would match this. And what matching means is the data that is being sent from a particular broadcast will land in the buffer provided in the matching broadcast on the other side. Because you're going to operate on that data, you need to know, where it's going to end up. You're not supposed to touch the buffers during the operation because it's a non-blocking operation. That makes sense. Another thing is that MPI cancel is not supported. How many of you are familiar with MPI cancel? It's not recommended to use it because MPI implementations don't like that function. So what MPI cancel says is, if you do an MPI I send, you're allowed to call MPI cancel and cancel it, saying that don't bother sending, as long as it has not been sent and already been received. And similarly, on the receive side, you could post an I receive and then cancel it. One use for it is legitimate use is that, let's say you don't know how many receives are going to, how many messages are coming into on the receive side. So you posted a bunch of receives, I receives, and then at the end you get a message saying that, okay, I'm done, I don't have any more data. So you have posted these additional I receives that are not necessary, and then you go and cancel them. That's a useful use for that. But there's also a cancel on the send side, which is not really useful. It's just there. But if you don't know about it, it's good that you don't know about it and you don't use it. But for non-blocking collectives, it's not supported at all. So non-blocking point-to-points can be canceled. Non-blocking collectives cannot be canceled. And these non-blocking collectives do not match with the blocking collectives, in the sense that if you call an MPI I broadcast, on the other side you cannot call an MPI broadcast. That is not going to match. You have to call the MPI I broadcast. Whereas in the point-to-point communication, you can match a non-blocking send with a blocking receive, or a blocking send with a non-blocking receive. That's allowed. And in fact, that might have been one of the exercises for you in your code also. One of the variations to try is to do an I send and then receive on the other side or the other way. So there it's allowed, not in the collectives. You have to make sure that you're calling either the blocking or the non-blocking for the matching purposes. So there is also a non-blocking barrier. I said all the collectives are provided, so there's also a non-blocking barrier. So the first thought is, of what use is a non-blocking barrier? Because a barrier is, when you call a barrier, you want to know that everyone has reached that stage, and when you exit it, you know that everyone has reached that stage. A non-blocking barrier means you have returned from, you've called an I barrier. What does that mean? So the idea here is to separate the notification of having entered the barrier from when you actually exit the barrier. So in the barrier, what happens is the barrier function as such is very fast, and on many systems it's hardware supported. So the barrier doesn't take time. The time goes in waiting for everyone to enter the barrier. So if you call an MPI barrier the regular blocking barrier, some other process might be somewhere else doing some other part of the code, and the time gets wasted in waiting for that person to enter the barrier, and then everybody goes out. In this kind of with the non-blocking barrier, you could, if your code allows it, if that makes sense in your code, you could call the non-blocking barrier and then go ahead with some computation, assuming that it's okay. It has to make logical sense in your code. And then when you really need to wait to know that everyone has reached the barrier, then you call your MPI wait. So what this MPI wait will not return, so the barrier semantics will be enforced at the MPI wait out there. So the wait will not come out until everyone has reached their non-blocking barrier. I barrier makes sense where you can notify that, okay, I'm entering the barrier, and then you have something to do after that before you can really wait for the barrier to come out of that barrier. But in the timing case, you need to, in that case which I mentioned, that you're starting this MPI W time, you really want all processes to reach that stage so that you're measuring a parallel operation, right? So it's not so useful, I think, in that case. So one thing is when you're operating in a distributed memory model, as I said, you rarely need a barrier because there's nobody stomping on your data while you are also doing it. But in a shared memory, if you have a shared memory thing, then you might need a barrier. And that's why UPC had it. So whenever you're dealing with some shared data structure is where you might need these kinds of